Let's Boltzmann Q&A how to apply diffusive scaling. So diffusive scaling is one of the possible scalings in the lattice Boltzmann methods. And the reason why we have to use scaling in the first place is because we have two different smallness parameters. We have delta t, which is the smallness parameter of the time, and we have delta x, which is the smallness parameter of the space, and they are here displayed in the characteristic diagram with the space direction in one dimension going to the right and the time dimension going here to the bottom. So there are two smallness parameters, and we expect convergence only if delta x, the space smallness parameter, goes to 0 and the time parameter goes to 0. And the scaling is required to link the two guys together in order to see convergence. So we have to link them in some way, and this opens the question, what is about delta x by delta t? So delta x has to go to 0 and delta t has to go to 0, but how is the ratio of them? So, and then there is one possible scaling. The one that we are not using right now is the acoustic scaling, where we take the units of the speed of sound. The speed of sound is a speed, so it has units delta x by delta t, and this is in acoustic scaling, it is constant, which means we have delta x going smaller the same way as delta t is going smaller. Because the speed of sound is now constant, both the Mach number and the CFL number in our simulation remain constant, and this actually is a problem because the lattice Boltzmann method has a Mach order 3 error, and this error will not get any smaller when we refine our crit and refine our time step in this acoustic scaling, because the Mach number remains constant. So, and if the Mach number remains constant, so independent of the resolution, then Mach square or Mach cube remains constant. And with this, the error remains constant, and so there would be no convergence. So now we know that we have to scale this in a different way. So what we have to do is we have to make the CFL number, with this the Mach number, smaller, and this is done by diffusive scaling, where we take the unit of the viscosity, kinematic viscosity, which is delta x by delta t, and take this as a constant. So if we take this as a constant, we see that delta t must be proportional to delta x square. This means if delta x goes to 0, the Mach number also goes to 0. So we have non-constant Mach number, so we have no acoustics anymore in our simulation. But this means the Mach number to the cube goes to 0, and so we get convergence despite the Mach error. Okay, so what do we have to take into considerations here? We have to have the setup for our simulation, where we start with a base simulation, and that is the one simulation from which we start, and then we add a scaled simulation. So the base simulation has a base crit spacing, a base time step, a base velocity, a base pressure, and a base relaxation rate. The scaled simulation has all these variables in the scaled way, and this will be scaled by a factor by a scaling factor beta. Okay, so this requires us to go, when we set the parameters for the scaled simulation, we have to starting from the base simulation, we have to scale, of course, delta x with beta delta b and delta t with beta squared delta should be tb. So this, of course, means we have when beta is smaller than 1, this means we have, of course, more lattice points, and we need more time steps. So this is not the only thing we have to scale. We also have to scale our boundary and our initial conditions, which basically means we have to scale the velocity u and we have to scale the pressure p. So the velocity u, if we take the units of velocity u, we see, of course, that is delta x and by delta t. And if we put this into the equation, we see that we have to scale the velocity by 1 over beta. And the pressure, so the pressure without, assuming the mass equal to 0, so in order to simplify units, then the pressure will be proportional to velocity squared. So what we have to change is to set the pressure, and the scale pressure will be 1 over beta squared times the base pressure. Okay, so this is for initial and boundary conditions. And now we also have the parameter of viscosity, and this is very fortunate, because so we control the viscosity by the relaxation rate. However, the viscosity remains constant because we use diffusive, we call it diffusive scaling, because viscosity is a diffusion coefficient, and the diffusion coefficient here is now taken scale invariant. So we see viscosity will be the same on both grids, and this means also that the relaxation rate will be the same in the scaled and the non-scaled version. Okay, so what is the cost of scaling? Yeah, when we have a base simulation with a given cost, which means usually a number of grid spacings, a number of lattice nodes, and a number of time steps that we have to take into account. And now, because this is the homework, we restrict ourselves to 2 dimensions. So if we say, for example, we have beta equal to 1/2, so we have now 1/2 the grid spacing from the base simulation in the scaled simulation. What then happens is that in each of the directions, when we say this is direction x and when we say this is direction y, in each of the direction we have to double the resolution, and therefore the number of nodes grows with the square of 1 over beta. In 2 dimensions, so obviously in 3 dimensions it would be the cube of 1 over beta. In the for the time step, the number of time steps, which we call big T here, because delta T is already scaling with delta x square, so we get for the time steps 1 over beta square. So basically what we would have here is 4 times more lattice nodes and 4 times more time steps, which if you count the operations that you have to do, it's then 4 times, which means it's 16 times more expensive to use here beta equal to 1/2, starting from the base simulation. So why are we doing this, and what are we actually expecting? So we are expecting convergence. This means that the error in our simulation is going to decrease, and this can be seen in a logarithmic plot. So please take into consideration this here is minus log delta x. So the error is here decreasing, and this is the logarithm of the error. Okay, so if we were to plot the error over the refinement of the grids, we would expect a linear function here in logarithmic scale, yeah, because the error would decrease with the convergence order Q, and we would be able to measure the convergence order from this plot because it's just the slope of this plot. So because we have to get this plot in logarithmic scale, what we have to do is we also have to place our simulations in logarithmic progression. So if we start from a base simulation delta x, delta xb, and we refine once with beta delta xb, the next refinement then should be beta squared delta xb. So the reason why we do it this way is because if we have this data in this exponential progression, as we call this, we can actually check our results with the so-called empirical convergence order. So this requires that we have some measure of the result. Yeah, remember always we don't know what is the real result. Yeah, and we want to measure the convergence. So because in order to compute the error, we would need have to need the actual solution of whatever we compute. For example, the lift value. Say we compute the lift value here. Since we don't know the correct lift value, we don't know our error. But with the empirical convergence order, we can also compute the convergence order without knowing the error. And this is this equation, which I'm not going to derive here. So you can look this up in literature. We have a measured order of convergence that we call Q, and this is simply the slope in this curve where we take the logarithm of now a combination of three different solutions: the base solution, a scaled solution, and a solution that is scaled twice. So it's the scaled solution of the scaled solution, and both of them have to be scaled with beta. So if the grid spacing in phi s is half the one in phi b, then the grid spacing in phi ss would be 1/4 the grid spacing of the base simulation. So some of you have as an exercise to compute the simulation in diffusive scaling. So I expect you to do at least 3 different simulations and measure your track coefficient and lift coefficient. In 3 different simulations, I do not require you to compute the order of convergence, but I may do it with your results. So thank you for listening.